All right, well, welcome everybody. I think we're going to begin now, so we don't waste any more time here. I'm really pleased to have Daniel Olago from the University of Nairobi talk today. He's quite renowned. He contributed to the Nobel Peace Prize in 2007 for the IPCC as the lead author in Working Group 1, the physical science basis. He has quite an extensive background in environmental geology and has worked on water issues in Africa for quite a long time, and I guess he's always been interested in water. In fact, it's notable that he was vice captain of the Nairobi University swim team when he was at the university, and he then was a Rhodes Scholar for Kenya in 1990 at the University of Oxford, where he got his PhD. So water has long been in his life, and today he's going to speak to us about water security in Africa's drylands. Daniel, it's all yours.
Yeah, thank you so much for that introduction. And you took me a little bit back to memory lane, you know. I'd forgotten all about my swimming activities in my undergraduate years here at the University of Nairobi. And I did actually join the swimming team in Oxford, but only for one semester. It was too cold, and I thought I'd reached, you know, the top of everything when I held one Olympic, medalist to over a 25-meter length of the pool, and I felt that was great. Cool. Okay. So anyway, let's get going. I'll be talking about the water security in Africa's drylands and looking at it from a groundwater perspective. And the outline of my talk is we'll look at the overall policy context, not just for Kenya, but Africa as a whole, and then look at the intersection of drylands and groundwater, and then why we need to develop that groundwater. And then I'll move on to the evidence base and what, you know, the issues are there, and the kind of approach that we have implemented to really counter some of these deficiencies that we see in terms of how it is developed and understood, developed and managed. And then we look at, you know, some of the aspects of groundwater research and development for water security. And then I'll just put up a little model to, you know, to close it off, a model on the science policy practice interface and how we can achieve more by working together. Okay, so when we look at Africa as a whole, we have the Africa Union, which is the continent-wide body that basically sets the political as well as economic agenda and social agenda for the continent at large. And the Africa Union came up with this Agenda 2063. And there are a number of areas and aspirations. But here we have the main aspiration being a prosperous Africa based on inclusive growth and sustainable development. And the goals are basically to have an environmentally sustainable and climate resilient economies, as well as communities. And among the priority areas, we see water security sitting right there in the middle of those priority areas. And we do know that water security is really related to some of the other priority areas which are highlighted there: in sustainable natural resource management, biodiversity conservation, sustainable consumption, climate resilience, disaster preparedness. All those really have some bearing on the groundwater resource in the region. And there are a couple of statements which are, you know, in this particular document. They're saying that Africa will be a fully water secure continent by 2030. So in essence, also linking up to the SDG goal number 6 on water. And this Agenda 2063 actually came before the SDGs, so that was maybe a visionary thing. And that new practices and technologies will be in place to ensure efficient use of water resources. And also for the development of new sources. And we'll see why that's important later on. The other thing is that we need to have functioning institutions and regulations and systems, as well as processes that are basically going to deal with transboundary natural capital. And that's the main emphasis of that particular one. Health, of course, is number 1 on the agenda. And so there's this issue of the need to accelerate access to water and sanitation. It's really very, very important because we know that here in Kenya, for example, more than 50% and up to 80% of people right now in hospital are there because they have consumed, polluted water or have some water-related diseases. So water is really very important, and sanitation goes hand in hand with that. And groundwater accounts for about 75% of the African population uses, and accounts for only 15% of the continent's total renewable water resource. And that's basically the only statement on groundwater in the Agenda 23 document. And also recognize that this particular statement is drawn from the Africa Water Vision, which preceded it, Africa Water Vision 2025. So groundwater seems to really, take a very low level pedestal in the entire water agenda. There's much more focus on surface water. Now, the Africa Water Vision itself then is looking forward to an Africa where there's equitable and sustainable use and management of water resources for poverty alleviation, socio-economic development, regional cooperation, and the environment. And that's really cool. And remember that we're just 4 years off, the mark of 2025. And when we had the MDGs, Millennium Development Goals, which preceded the Sustainable Development Goals, the target was to have a 75% reduction of populations having no access to a hygienic and suitable supply system for drinking water, as well as sanitation system. We know that these targets were not achieved, and in many cases, and in many areas, probably not more than half of those particular targets were achieved. And these are some of the issues that we have. And the Africa Water Vision wants to reduce this by 95% by 2025. And that is not happening, and we will be able to see some of the reasons why. We have another related strategy here. If you recall, we talked about the need for new technologies as well as new practices also to enhance water supplies. And we have another document here called the Science, Technology and Innovation Strategy for Africa 2024. And we see here that, water plays a very, very key role in this particular strategy. So it recognizes the essential and cross-cutting contribution of water across all the 6 priority areas, which include eradication of hunger, prevention and control of diseases, communication, protection of our space, living together and building society, and wealth creation. And there are all these flagship programs which ought to have been instituted by the different agencies, whether they're at the continental level or at the regional level or at national level, that were to basically, implement activities that would push us towards the goal of achieving those priority areas, at least in the water sector, is what I'm showing here, but also in various other different sectors. Okay, so let's move on now to our drylands here in Africa. And anywhere you see on this particular map, really, that isn't green is really, or blue are the lakes, is really the dryland areas. And we have the, savanna and the desert areas as well. Now, in these areas, we have very high climate variability and generally fairly low amounts of rainfall. So that's one of the main issues that we face. The other thing is that the groundwater potential in these areas is extremely variable in space, in time, vertically below the ground, in terms of quality as well as quantity. So it's not it's extremely heterogeneous. It's not uniform, and it doesn't really follow any particularly clear patterns, as we shall see later on. There's also an increasing demand in these areas and also increasing water scarcity, and I'll go a little bit into that when I move on to focus on Kenya, which is what I'll be concentrating on in a little while. There's also low water supply and sanitation coverage in these areas. And in Africa, in most areas of Africa, you'll find that people living in cities have, much better access to water resources than those living in the rural areas, partly related to, of course, the fact of economies of scale. The rural areas are sparsely populated, the dryland areas more so, and it could cost as much as 4 times to get water to one person in the rural areas as compared to one person in a city. And so we also have these incidences of water-related diseases, mainly related to microbial contamination of the water resources from a number of agents, human, but more so livestock as well as wildlife. So here in Kenya, our country is 80% dryland. And that's all the areas, again, excepting those that are blue and green. So, a huge swath of the country is really dryland. And 38% of the human population of the country is actually found in this area. We have high climate variability. So it is the coefficient of variation of rainfall is extremely high in this area. And the rainfall tends to be generally less than 600 millimeters per year. And these areas are therefore subject to frequent droughts. And in fact, the droughts are becoming much more frequent. And these droughts are related to the interannual droughts or interdecadal scale droughts related to ENSO. But we also have seasonal droughts. And one of the main problems that we're experiencing now is that the intensity and magnitude of these droughts is increasing as well. And we are even getting successive seasonal droughts. So they build onto each other and the impacts therefore become cumulatively much more devastating. These areas are also subject to flash floods, especially during the ENSO years. They are also characterized by, highly intense rainfall, and much of the rain that they receive in a year may actually fall within 1 or 2 days. So in essence, these are some of the issues that are being faced. In some other parts, like in the Northwestern part where we have the Turkwell River, which basically originates from Mount Elgon in the humid tropic equatorial region here and flows 300 kilometers to the north, can also generate flash floods. So there's no signs of rain here. It's all coming from this very humid area. And we have a small town that straddles the lake, and it tends to, suffer from these flash flood effects. And groundwater is often the only source of safe water in these areas. The other thing to note is that pastoralism is a very important livelihood activity. And as I mentioned, we have a lot of livestock in this area, and they also do need water. And we do have a lot of conflicts related to water because of competition for that particular resource. The other thing is that the people who live here, these 38% of people living in the drylands, have the lowest development indicators in the country. You know, they're the poorest people. They have the least access to services, the least access to anything really within the country. So they're the worst off. They tend to be marginalized in many cases. They don't have any infrastructure, and it's difficult also to move from one place to another. So let's come to the issue of what exactly is water security. And we can see, first of all, in the picture on your right-hand side, the need for the water in these dryland areas. So this is in Turkana, which is in the northwestern part of the country, where we've been carrying out some research recently on a groundwater system that is strategic to an urban town in the area. And so this is a little bit out of the town area. And you can see that during the dry seasons, they have to scoop sand out of dry riverbeds and get to the water table and then harvest that water. And you can see also that those who are collecting this water are mainly children and also women. And this takes them away from other activities like going to school and getting a good education and other things like that. So it just shows that there really needs to be a strong focus on these areas to ensure that the livelihoods of these people, their well-being, and the opportunities for advancement are actually attended to. So water security is defined by UN Water as the capacity of a population to safeguard sustainable access to adequate quantities of acceptable quality water for sustaining livelihoods, human well-being, and socio-economic development, for ensuring protection against waterborne pollution and water-related disasters, and for preserving ecosystems in a climate of peace and political stability. And so what we see here, if we peg this against the SDGs, is that there's a lot of intersection across the SDGs. We can think of SDG 6 on water intersecting with SDG 1, no poverty, SDG 2, no hunger, SDG 3 on human health. We have SDG 5, I think it is, on quality education. We have SDG 10 on inequalities, and we have SDGs 13 on climate action, really related to tackling the issue of the climate variability and how it impacts the groundwater resource, and also 14 and 15, life in water and life on land. We know that these groundwater systems are quite important in sustaining some particular types of vegetation ecosystems. They are also important in coastal areas where fresh groundwater discharges into the oceans, and they support some very unique assemblages of aquatic organisms. And the partnership's role as well when we are looking at the issue of peace and political stability. So the need for developing our groundwater resources for water supplies is quite important. I've highlighted some of these and maybe I'll repeat them. We have low access to adequate, reliable, and safe water, and this is with reference to the dryland regions. We have also very rapidly growing urban populations as a consequence of the devolution of power. Now, what happened is that Kenya changed its constitution in 2010 and moved from a central governance system to a devolved governance system. And so now we have 47 counties, much like the US has its states with their governors. And this has actually made the urban centers really grow in each of these 47 countries. And most of them, most of these urban centers are in the drylands. And here we see other rising competing demands. For example, Kenya recently, in the past 10 years or so has discovered oil. Okay, we know what's happening with oil now, but there we have discoveries and they're still thinking of exploiting it and looking for water resources to do so. In these areas, we have in some of these areas, we have a few seasonal or quasi-perennial rivers that flow through them, and these are now coming increasingly under irrigation agriculture, and which in many cases is really unsustainable when you consider the groundwater resource. And commercial activities are also on the rise, so there's a lot that is happening in that area. The other thing is that the drylands host 70% of the livestock population in the country. So that is huge. And livestock production itself produces about 50% of the agricultural GDP. And again, these dryland areas host 90% of our wildlife, and this supports tourism, which generates about 12% of the national GDP. So the dryland regions are also very, very important. And we recognize now that it is also a critical resource for buffering climatic and other risks to future water supplies. And more so in the context of these very rapidly growing urban centers, growing at the rates of 6 to 7% right now per annum, as well as very important in terms of looking at how we are going to preserve our livestock as well as our wildlife in these areas. This particular table that I put here just shows, demonstrates in more detail some of really the dire aspects that we have there. In what I've marked in red are the urban, small urban towns in the dryland areas. And right at the bottom, you can see that our National Water Master Plan, has a certain target for water supply in terms of liters per person per day. And the target is to, get every person have at least 119 liters of water per day available to them. The real situation right now is that in places like Lodwar town, they only have access to 10 liters per day per capita. In other towns like Wajir, there's absolutely no water supply, and they get most of their waters from wells that they have dug on their own or from boreholes which have been put in place there by charitable organizations. And even where we do have water supply systems, there's a huge amount of loss through leakages, water theft, water wastage, inactive connections, vandalism, some of which I've personally seen happening, and a lot of other, sweeping problems which indicate that institutions need to also, ramp up the act and get things moving to ensure that we really meet the targets of the Africa Water Vision, the Agenda 2063, as well as the SDGs. So what do we know about the groundwater in our dryland areas? So we're going to look at the evidence base a little bit. There are two principal factors here. The first is that groundwater is an insufficiently understood asset. And that rings true today as it was in 1996, when Mike Edmonds stated that groundwater development in the rift, the central Kenya rift, has proceeded without an adequate understanding of the water balance, nor knowledge of the amount of recharge. And under the point number 2, illustrating the threat and multiple anthropogenic and natural factors, Becht and Harper noted that the quantity of obstructions from the Naivasha catchment is not known and can only be estimated from obstruction permits or known area of cropland and known requirement of crops. In any case, such groundwater may or may not be contiguous with lake or with inflow water. Now, not much has actually happened to advance this understanding. And this is, for a number of reasons. Number one, groundwater is invisible. And therefore, people find it very hard to relate with groundwater. And when we talk about, you're taking too much out of the ground and this system is going to dry up, they can't see it. They can't see that dropping level. They also cannot see it when they are polluting it. And the effects of pollutants that get into the ground and consequently into the groundwater system depends on the system. And in some cases, it may be fairly rapid. It may take a couple of days or weeks to get into the actual aquifer system. But in some cases, it may take, 10, 20, 30 years. And the other problem with the groundwater system is that once it's polluted, it is very, very difficult to remediate that. You kind of just lose your groundwater forever. So how do we develop our knowledge about groundwater? Well, we basically talk about aquifer characterization. And so we assess a number of different factors. We look at the hydrogeology of the area. We try to determine the type and size of the aquifer to understand its geometry and the depths at which the groundwater occurs. And in many cases, there could be multiple levels within a particular area that you can actually target and get fresh groundwater. We need to understand the recharge and discharge and hydraulic characteristics. And the recharge is, of course, very, very much strongly linked to the rainfall amounts, the distribution, the intensity, the types of soil and the rates of infiltration, the surface rock geology relating to things like fractures, if you're in limestone areas, to karsts, and all those different factors have to be taken into account. We also would want to know how susceptible they are to pollution, to abstraction, and to saltwater intrusion, because all of these will help you to determine, what protection measures are needed, how much water should actually be abstracted, what kind of monitoring systems need to be in place to ensure that saltwater intrusion is not occurring. And we also have to align this with the intended use and sustainability. So we have to determine how much water there is, for how long, it's going to be there, and for what purpose we want to use it for. And very surprisingly, only one small aquifer in Kenya has been satisfactorily characterized. This is the Barito Aquifer. And this satisfactory characterization relates to what our Water Resources Authority says we should know about an aquifer. So only one tiny little guy, this one sits on close to the coast of the Indian Ocean. And that is really the best known aquifer system in Kenya. So let's look a little bit more at the evidence base. And nowadays, we have a lot of ways in which we can generate information, and we generate information at fairly different scales. Here we have, two continental scale maps. On the right, at the top, is a map of the geology of Africa as a whole, so the different types of rock systems that we see. And this gives us some idea about the types of groundwater aquifers that we can actually find in these particular areas. And the figure on the left basically shows the estimated groundwater storage capacities in the African continent. And when one looks at these maps, you'll say, oh, well, these are really good, and we'll be able to, get whatever groundwater we want in these particular areas using these maps as guides. But then these scales, as you get more granular, as you move from the regional scale to sub-regional to national, sub-national, and then eventually local, you will find that the complexity increases. And in fact, the generation of these maps at continental scale, which ordinarily ought to derive from the little bits and pieces of information that we get at local level, are really not in tandem with reality on the ground.
Good luck.
All right. Then the second bit is the issue of the complexity. the hydrogeology is really very complex. If we look at that map on the top right-hand side, we see that we have the volcanics, and volcanics are predominant mostly in the East African region and associated with the East African Rift System. And then we have what are referred to as the basement rocks. These are rocks that the order of about roughly between 500 million years to 300 million years old. And they are metamorphic rock systems. And then we have the unconsolidated and sedimentary rocks, which are normally occurring along the coastal zone areas and across parts of the Sahara and other areas. And when we get down to the very, very granular level, we will find that we have really a very complex hydrogeology. And so these maps, while they look very good, you really need to get on the ground and learn a little bit more about what is happening. We have issues also with how climate and recharge really, that interplay between climate and recharge. And these particular maps that you see, they also talk about groundwater storage, will have some presumptions about how recharge is occurring. But recharge is a factor of many different things: soil cover, the type of rocks, the fracturing system, slope angle of the terrain, and many, many other factors. So, and we still have a lot of uncertainties about these at all those levels. So here I'll give you an example from Kenya. We see here on the left-hand side, this figure is showing us where we have drilled boreholes. And we have been able from those borehole drillings to come up with some quantitative measure of the transmissivity, that is with which well, not really the ease, but how much water can be transmitted by an aquifer in unit time across a uniform surface of 1 unit square area. And we see that there are really very clear knowledge gaps. First of all, recognize that this map on the right, the transmissivity map, is built on data which is derived from the map on the left. And you can see that if you recall the map that I showed you on the dryland areas, you can see that there's very low borehole density in the dryland areas, very little information to go on. But when you come to the map on the right, you don't have any indication that there is, the differences in availability of data across the country. All you see are very nice looking maps that tell you that, in fact, in our dryland areas here, we really do have a lot of groundwater, and you can see that from the very, very high transmissivity values, ranging from orange to pink and purple. Okay, so it's and that is not actually correct. So the other thing is that this map on the left showing the boreholes database, some of these boreholes are very shallow, some are like 20 meters deep only, others are go up 50 meters, others 100. Some are very deep, 200, even 300 and 350 meters. Again, that is not apparent when you look at the transmissivity map on the right. So there are a lot of gaps that exist. And I'll give you an example here of what we call the Barito Aquifer and the Lapset corridor dichotomy. Now, the Barito Aquifer is an aquifer, and it's a large aquifer that basically kind of lies in this particular system here, although of course it's not as expansive and the yields are not really as big as they indicate throughout this particular area. The Lapset is the Lamu Port, South Sudan, Ethiopia transport corridor. So these Kenya, Sudan, and Ethiopia have actually started building a huge infrastructure corridor, road, rail, and a port at Lamu here. that will be, gateways to Ethiopia here and to Sudan on this side. One of the things that they did not take into account is, how much groundwater there is actually in this particular area. And so to their consternation, following, the development and the plans for, the roads and railways and everything that will, be built along this corridor, as well as resort cities, which are planned in a lot of these dryland areas, they found that there is insufficient water when they actually went to the ground. So these kind of maps are really not very helpful to us. They do look nice and colorful, but at the end of the day, they are not really helping us to advance our understanding of the groundwater systems to the extent that we can apply them to development for sustainability and for the welfare of our communities. Here we have another example, and this is the Mount Elban Aquifer. Here I've done a little bit of work, but only on the Kenyan side and not really that extensive. But one of the things that caught my interest was how the aquifer boundary here, which is in red, was actually defined. How was it exactly defined? And when you look at this boundary as well, there's some aspects of it that appear to be a little bit haphazard. Now, this is Mount Elgon right here, so, quite wet and whatever. So the entire mountain is being taken as an aquifer system, while, of course, we expect that mostly we have the recharge zones and then the discharge zones where the water now emanates as springs, and there could be further extensive zones elsewhere. And so this particular outline, to me, seems to be arbitrary. There's no, they call it confirmed aquifer boundary, and I've got absolutely no reason why, because we have, lots of water boreholes out in this region here in Kenya, and all the way here, which are really still related to the mountain volcanics here, and at the intersection of the metamorphics and the volcanic rocks as well. So we have these kinds of issues. So these maps are being presented, but there's really nothing at the back of the data that supports that. Here now, let's look at some of the more recent scientific assessments that we've had. And these ones generally, I refer to them as black boxes. One example, which is normally touted as, the big thing now, is the data that we get from GRACE, the Gravity Recovery and Climate Experiment Mission. So this satellite, what it does is it basically captures data on the variations in gravity within a particular area. And that gravity variation is related to the amount of water that is held within more or less, let's say, the surface top, maybe 30 meters or so of the Earth's surface. So it's really sensitive to mass changes, but over very large spatial scales, so on the order of 100,000 square kilometers. So it fails to provide us with groundwater storage change estimates at scales which are relevant to most of the aquifer systems which we are interested in. So the other thing is that we had some work which was also done by a company called RTI, and it was reported really, I think, the world over, that they had discovered vast groundwater reserves in northwestern Kenya. And the estimations here were that we could have as much as 250 billion cubic meters of water in this region here, as opposed to roughly about, if I recall correctly, roughly about 30 billion cubic meters, which were estimated for the entire country as a whole. So all of us were extremely excited about this. Okay. But we wanted to know a little bit more about how this technique works, and what is really being evaluated, in this WATEX system, which was used to generate it. And the RTI were really unable to share anything with us. They said that the work is proprietary. The way in which they designed their toolbox was not open to us to really see and understand what is going on. In any case, the government of Kenya went ahead to drill some 3 boreholes in some areas where this vast groundwater reserves were supposed to occur. There was a good strike in an area which had a lot of fault fractures systems. And the other 2, which were in the sedimentary basins, which would be the ones that were thought would hold the most amount of water, we ended up with saline water in those areas. So, of course, the estimates need to go down, but it also shows us that a lot more work needs to be done at the aquifer system scale level in order to understand what is going on in those areas. Okay, so we move on to the policy management and practitioner approaches, which basically undermine the evidence base. So if we kick off with the policies, we have still a very old water policy, which was developed in 1999. But this particular water policy has now actually been updated, but it has not yet been approved by the government. So, we still don't really know what is in that particular policy. But I do recall that in the year 2012, I was part of a team that developed a national groundwater policy. And that one seemed to have been shelved, and they said, well, it should just be incorporated into the national water policy. And that policy has not come out until now, and we are still not sure to what extent it has taken into account the issue of groundwater. Then we have Kenya's Water Act, this 2016. This one was basically a new act, which, well, not really new, but it was developed after the Act of 2002. And this Water Act, along with many, well, almost all of Kenya's other acts, were basically reformulated so that they fall in line with the Constitution of 2010. But it also gave the opportunity to come up with new ways of looking at the water resource. And yes, there's something there on groundwater management and other aspects like that, but it probably doesn't quite do enough. And maybe because it was developed without actually a policy to guide the development of the act in place. Then we also have the National Water Master Plan of 2030. And this National Water Master Plan has a very strong bias on surface water resources and very minimal reference to the groundwater resource. And they also said that that they couldn't really say much about the groundwater resource because there wasn't really enough data. Okay, so we see that here there's inadequate policy and also inadequate governance focus on groundwater. And even within the Ministry of Water, and this I think is a common occurrence in almost all the countries in Africa, is that it receives the least amount of budget as compared to surface water. In terms of management, we have issues with institutional management. It's very weak. We have very institutional management regimes. We have outdated strategy documents. Strategy documents normally are put in place to last on the order of 5 to 10 years, but a number of them have not yet been renewed. Coordination and management structures within and across jurisdictions are weak and lacking, and this is really a big problem because groundwater or water of any kind really and cannot, they cut across jurisdictions. And there may be slightly different or maybe totally different management systems in one county as opposed to another county. And that creates a lot of conflicts. Then there's also the issue of low technical capacity in management. So one of the main concerns which we have right now is that in the counties themselves and the people who are mandated to actually manage water resources within their jurisdictions may not even have training in the area of water. And if you look at the county integrated development plans, which are the 5-year development plans that the counties produce and which align to the national development plans, they talk a lot about developing, drilling new boreholes and developing water supplies, but they don't have any information on the groundwater resource. And we'll come back to that again later on. And then when we look at the issue of the practice, we have very limited literature review being undertaken. We have very old geological maps which are being referred to still up to date without any updating of the geological maps, despite the amount of work that has gone into updating the geology of the country. The other point is that in practice, people, when they're looking for where we are likely to get some groundwater, they basically just go out with a thermometer and carry out a vertical electrical sounding at a point, and get the data and say, okay, yes, here you can drill down to maybe 100 meters and you'll get to the aquifer and get some fresh water. But nothing else about the aquifer characterization, which I talked about earlier, takes place during these kinds of exercises. The other thing is that we have untrained personnel who are carrying out things like geologging. And so we get some very strange logs where they actually do keep logs. In many cases, they do not keep logs of the drilling of the materials as they're drilling through the rock formations. But I've come across, limestones being described as granites and really other crazy stuff. So even if there were logs available, they are not reliable data, and because they were logged by untrained personnel, by non-geologists. We are also constrained in terms of the type of equipment that we have in place for drilling. Many of them cannot really go to depths greater than about 300, 350 meters at the most. And we would wish to be able to explore some deeper aquifer systems that may exist at depths of maybe 600 meters or more, much similar to the kind of aquifer systems that we see in Northern Africa, like the extensive Nubian aquifer. So our approach has been to basically look at the aquifers through a systems approach. So we assess all our existing geological, climatic, hydrological, and related info on environment and other aspects. And then we carry out a detailed field mapping, boots on the ground, before we get on to using other techniques like the geophysical and others, so that we can better understand when we come to interpreting what is happening. And then we look at it from a regional perspective down to the local perspective, but we also try to understand how that particular environment has evolved through geological time. And that is also extremely important in enabling us to understand how that aquifer system could possibly be laid out even before we actually carry out our geophysical work to get a better understanding of what that particular system looks like and how it is possibly layered. And then we also need to be able to establish environmental monitoring programs and also a data and information system, which is open and open access, so that other people can benefit from this data. And we hope that this kind of data can be used and built up through the years. Here I have two pictures, but I want to talk about this one here, particularly on the left. This is in the coastal area of Lamu, of Kwale in the south coast area of Kenya. And this entire area had actually been mapped out as being a coral limestone area. And this little exposure here was really hidden under bush. And when we spotted it, we realized that it's actually a sandstone. And this was the beginning of some big discoveries, which I'll be talking about later on. But it's very important to have boots on the ground. If you look at these old maps that were done in the 1950s and 1960s, they weren't able to do it at a very high resolution, at very high scales. And so all of these kind of things, and we'll see why this one was a really particularly important find and why it's important to really get on the ground and look at your systems and understand them in a better way. Okay, so this is related to that particular picture that I was talking about. What happened here is that this sandstone was discovered in this particular area here. And it got me thinking that perhaps in this particular region, we have a couple of paleo channels, which were formed somewhere between, the Jurassic and the Pliocene times when these ridges actually came up. And therefore that there would be these kind of old and buried river channels that likely would hold a lot of water. So we're able to map, given the time that we had, we could not really properly constrain the marginal extents of these systems, because most of this area is actually covered in sand. And but we're able, with the geophysics, also to kind of now limit some of these. And we actually found that there were 2 paleo channels in these areas of high yielding aquifer systems. And we also found that there were 4 different fault systems which were running in the northeast southwest direction, all the way down to the coastal zone. And that also had a lot of effects on where and how much of groundwater you are able to get in these particular areas. So there are a couple of boreholes which existed in this area previously, and but they did not know that they were actually drilling into a paleo channel aquifer system. But when you look at the logs of these boreholes, and these ones were actually, the logging was done by some competent geologists, you could see that in fact what we're looking at were these kinds of sediments right in there. And here we can see that there were some moderate yielding aquifers in this area, but none in this particular area. And the county government recently now came in on the basis of the data that we have here, and they drilled 1 exploratory borehole within this paleo channel and got a very good groundwater yield in this particular region as well. And these ones that are out here are controlled by the different fault lines. So there's one up there and another one somewhere around here, and another one at this level here, at which are the structural controls for the groundwater in this particular system. So that is one example. The second example, and I'm now kind of getting close to the end. Here this is in the Northwestern Kenya region. Right here we have Lodwar town, which is this town in this dryland area. It receives roughly about 220 millimeters of rainfall in a year, but it has this river that runs through it, a quasi-perennial river called the Takwel River, and which originates from Mount Elgon in the humid south, 300 kilometers to the south of this particular area. So here we basically started from ground zero. Here's a town with a population of about 80,000 people. They have boreholes in these areas, really most of them next to the rivers, and that is what they use for their town water supplies. But there was basically no data on those. They were using the wrong approach in terms of accessing the water resource. What we did find is that the fresh groundwater occurs in Holocene sediments, which had previously not been mapped. So we mapped these sediments first. Before, if you looked at the map of this area, it would all have this color that you see here of the Turkana grit and the overlying, sediments. We're able to map out these, and we then carried out further studies. We noted, of course, another feature here, which is a dolerite dike. And it is a major control factor because to the east of it here, it acts as a kind of a barrier that stops leakage of groundwater from this region to areas to the west. And therefore, this is one area which really has a huge amount of groundwater in this particular system. And for the entire system, we found that the amount of water held in this system is roughly about 1.3 billion cubic meters. So there's quite more than enough water there to support this particular town. One of the main other finding here is that the dominant recharge pulse is from the Takwel River and secondarily from the Kawalase River here. And that means that if we interfere with this river, especially the Takwel River, which has a catchment area of 23,000 square kilometers, then we are going to, seriously affect the sustainability of the groundwater system in this particular region. The other thing that we found is that there's also a distinct seasonal variation in water quality, and that the quality of the water in the wet seasons went down quite rapidly in the boreholes which are closer to the river than to those which are further away. And that would give some indication or some idea about how to manage the groundwater supply sources under different rainfall regimes and flooding regimes. So here are some of the things which we were able to come up with then. On the left is a water quality index map, which now one can more or less, with a high degree of confidence use to determine what kind of water quality we would get in the areas around here and which particular areas really need to be totally avoided. You'd be wasting money going into these areas to try and look for water resources. And we have also been able to come up with an aquifer model here system. And this is also useful for planning purposes in this aquifer system, which has three aquifer layers, which are well all connected. So anyway, let me move on to closing my talk. There's some ongoing programs in Kenya, which are good and moving in the right direction. We have the Kenya Groundwater Mapping Program, which was established in 2014 to basically increase our knowledge of our groundwater resource. And some of the good things about it is that they wanted to validate some of the recent studies, like the one I mentioned about the big, aquifer systems in Turkana, and that is still something that is going on. They also were paying attention now to nationwide groundwater investigation with priority given to the dryland counties. And also developing management plans for aquifer systems. And this is one which is actually now rapidly ongoing, which is very, very good. And in fact, there's a World Bank funded activity right now to come up with ways of better managing the aquifer systems within the dryland areas. We also need to integrate the socio-economics of groundwater resources. And I didn't really touch on this aspect, which is also very interesting, but it's another talk on its own. But we do note that there are gendered aspects here, and there are socio-economic aspects that also feed into the ground, how the groundwater resources are managed, protected, and how the waters are distributed to different economic classes of society. And we're also looking at incorporating the integrated water resources management principles, because we are seeing in many of these areas, there's a big connection between the surface and groundwater systems. Managed aquifer recharge is something that we're still, not yet applying here in Kenya, and but there are proposals to to implement them gradually, incrementally in many areas. But again, this means that we need to have a much better handle on the distribution of potential aquifer systems in our dryland areas. Sustainable land management is also important. It started picking off around 2010, and it is now a practice that is being enhanced because it has been demonstrated, particularly in Malawi, that when you employ sustainable land management principles and practices, you also tend to increase the amount of storage of groundwater in shallow aquifers and also increase the recharge to deeper aquifer systems. So in essence, this particular diagram here shows us on the left, and you can read this paper of mine later on to get maybe a better handle on it. But here we are looking at a policy objective of the government that everyone should have piped water either into their homes or into an area that it is very, very easy for them to access, and this is clean and also treated water. And what we do see is that if we look at the dryland towns like Wajir here, Lodwar, and Msambweni, as compared to those that are in the humid areas like Kisumu and Nakuru, we see that they have kind of different profiles in terms of how, where they get their water from, which are the most important water sources, and how many people actually use those different water resources. And this is the kind of information which is important that tells us that, one size doesn't fit all, that we need to have unique solutions which are responsive to the uniqueness of a particular area in terms of their water supply needs. But in general, if we look at the diagram on the right, there are a number of elements which need to be taken into account. And maybe starting from the middle out here, we have to note that we need to look at surface water and groundwater in a conjunctive manner. And this includes also looking at the climate system and how it interacts with all of these factors. The environment is very, very key in terms of, how much water we're going to get in the system and how safe it is, whether it be surface water or whether it be groundwater. Now, groundwater and surface water also, I mentioned the polluted surface waters that we generally have, but the groundwater systems may also have some natural challenges like high levels of fluoride, for example. And depending on the area that you are in, we can also implement small scale and discrete treatment systems to tackle some of these problems. They would have to be specific because in certain other areas, what we have is a problem with high levels of iron and manganese, and in others, many different other issues. What we need to have is, of course, to continue on with working on the issue of research and innovation, to implement monitoring data and information systems for all our aquifers and continue monitoring them in the long term, particularly given the future risks and the scenarios that we are facing under changing climate, rapidly increasing human populations, and other factors. And that interdisciplinary and intersectoral collaboration is key. And you can recall the intersections that I talked about between, SDG 6 on water and multiple other SDGs, which means that we really need to look at these in interconnected manner. So this is now my last slide, and I'll basically finish with this. This is now a model which we are implementing for the REACH program, in which we are carrying out in Turkana as well as in Kitui. And this is in a way how we are trying to bring together, or we are bringing together the science, policy, and practice interface so as to kind of impact strongly on the issue of the water security in these particular areas. I can say that it is working well. At the bottom here, we have generated the evidence, and let me use Turkana as an example. We have generated a lot of evidence on the groundwater system. We have done some training, and we have demonstrated some decision-making tools, one of which, for example, illustrates that if there's any kind of agriculture that is taking place upstream, irrigation agriculture, then it is likely to compromise the amount of water that we have in that particular aquifer system, for one, leave alone pollution. And under climate change, it's a no-go zone for that particular aquifer system. And in terms of working with the practitioners, and there are many that we are actually working with, they are now using our project research outputs within the programs that they have, and they're exchanging information and data with us. They're building climate resilient measures into their long-term planning, and for these particular areas, in the areas that they're working in, and also in their own internal policies and guidelines, and also taking these into account in terms of the services and activities that they're implementing for the communities. Now, at the policy level here, we are interacting mainly with the ministries of water resources, the Ministry of Environment and Natural Resources, the Turkana County government, and members of the county government in this area. And the idea is that these will help us also to upscale our findings and procedures and processes to other counties within the region. And I can say that, for example, in Turkana County, we have had a major influence on their climate change policies, on their water policies. And we also developed for them a 10-year water delivery plan. Remember that their town is 100% reliant on groundwater from the aquifer system, which I just described earlier. And they are really calling us to assist them and give them more support in terms of the policy and regulations at their level, but also at the national level, these aspects are also being recognized. We also have national bodies which are not necessarily government bodies as such, but they could be related. These are the Water Resources Authority, the National Drought Management Authority, the Kenya Meteorological Department, and other agencies like the environmental management agencies. And we're working with all of these as well, as they are reviewing their policies, whether they be at national level or whether they be institutional policies, to be able to also incorporate some of the principles that we are using, and also to lobby the county governments to increase an allocation of resources for water, groundwater research, and also water supplies. And then more generally, we are reaching out to the Africa level through the Africa Ministerial Council on Water and Environment, and other strategic partnerships with other agencies that I may not maybe mention now. So thank you very much. I think I'm going to end my talk there.
Thank you very much. That was most interesting. I'm afraid a number of our students had class and sort of had to leave, but we have a few more minutes for questions if anyone has a question. And Daniel, you have to unmute yourself.
Oh, okay.
No, I was just applauding, and I appreciated your talk very much. I want to apologize for my shout out in between. My mic was briefly on because I came from another meeting. So sorry about this. As I'm an atmospheric scientist, and I'm quite impressed about the challenges you outlined. And I had once a hydrology class with Professor Sontag, who determined the water age of the Saharan desert. And as I looked at your data, what you showed and what you achieved, I was wondering how much that information could guide you, being not a hydrologist, the usage of the aquifer waters, or how much age information do you have? How old is the water? I grew up in the 90s saying if it's very old, then you can exploit it maybe more or so. I'm just as an outsider. Thank you again for this nice talk.
Thank you. Yes, so the last aquifer system that I mentioned, that Turkana, the Lodwa aquifer system, we actually have dates on the age based on tritium, not carbon 14. So, but what we do know is that any water that is older than 1950 in this area is highly saline and totally useless. And so the fresh water is younger than 1950. And most of it, it looks to have been recharged in the 60s and 70s.
Thank you.
So we have a few more minutes. If I have a question, if unless someone else wants to jump in here and ask something, but so what's happening with the African lakes, the Rift Valley lakes? Water levels have been going down, and now in many cases they're going up. And at least for Turkana, you know, what does this have to do with groundwater, if anything?
Yes. All we can say is that everyone is really just thinking through these issues. The government had a task force that went to look at what was on the ground. These lake levels started rising in 2010. And I was in a group of scientists I think it was in 2011, where we petitioned the government that we really need to study this phenomenon. Can you put aside a little bit of money so that we can carry out various different types of analysis, including climatic, hydrological, and groundwater isotope analysis, so that we can pin down where this water is really coming from? Well, they never really reacted. But last year, you know, well, over the past few years now, but more recently than before, the national park in Nakuru, the gate has been submerged. Hotels in Baringo, underwater, schools and hospitals. So they got concerned. But what I think could be the reasons, because no one really knows yet, because no one has been able to do a study, is that there likely has been a change in the PE ratio. That I think is the main thing, because we don't really see that much increase in precipitation. So it could be that there's been a reduction in evaporation. And the second thing is that there could also likely have been a shift in the pattern of rainfall, so that where we're getting most of the rainfall occurring is not in the traditional, you know, spatial areas, but it has actually shifted to areas where then they are recharging the groundwater systems. Yeah.
Okay. So there, Cindy Lee has a question here, and should I read it, Cindy, or you want to ask?
No, you go ahead.
So Cindy's question is that you briefly talked about Africa as a whole, then naturally focused on Kenya. But there's currently an argument between Egypt and Sudan versus Ethiopia with regard to the influence of the Grand Ethiopian Resistance Dam on the Nile. How will this dam affect the water needs of Egypt and the Sudan, where groundwater is a smaller resource than in Kenya? Do you have any thoughts on how these and other intra-African differences might be resolved? Oh my goodness, we have a few more minutes.
Okay, yeah, so this one is quick. So yes, that story is a political one, because you see, with a dam, you can control how much water goes down. And I think Egypt is really not happy with that. And once you have a dam, you kind of regulate flows, and maybe Egypt and Sudan had already, you know, put in a regime for managing their flows within their own countries. So I think that's one of the reasons why they're very much concerned. I think it is more about just you know, national security more than anything else.
You don't think it's about water needs? I mean, if Egypt doesn't have water, I wondered how you can what your thoughts were on how intra-African differences can be resolved. Is there a body where these questions can be discussed? A governmental body?
Yes, we have the Africa Union, which is supposed to be discussing these issues. I understand. I'm just saying that the root cause of this is really about national security. So, building a dam in and of itself that will not necessarily deprive someone downstream of the amount of water they were getting previously, except at the point at which you are filling in that dam. Okay, but you can allow for releases that allow them to continue to get the same amount of water that they were getting prior to the time that the dam was put in place.
I see.
Yeah.
Josie, I had a quick question. Can you hear me?
Yes.
Oh, thank you, Dr. Olago, for a very interesting talk. Huge issues. In terms of, if you do some simple arithmetic, like how long an aquifer will last, like for example, Lodwar town, you said there may be 1.3 billion cubic meters of water, whether it's potable or not, I don't know. And you've had 80,000 residents. How long would that last if it was not being recharged? Because we have in the US, like Las Vegas, is depleting its groundwater, and it can't go on forever. Long Island, we're completely dependent on groundwater. If you look at Jakarta, Indonesia, they use groundwater for that huge city, and that's sinking down, and now it's been flooded from the sea. So with that, you don't have that problem. But I mean, what would be, you say you have abundant water, say for Lodwar town, would that be 100 years or 500 years, or you don't know?
We did a little bit of a scenario of that on a small portion of the aquifer system. So let's say about a quarter of the 1.3 billion cubic meters, and we realized that it would probably run out in about 5 years' time.
5 years.
At the current rate of abstraction.
Well, that's
so
pretty
and that, yes, absolutely, and that is why it's really important that you look at we get a really good handle on the recharge system and ensure that we are only abstracting the rechargeable amount of water, not mining the aquifer system.
And what's the human population growth of Kenya?
Kenya itself, I'm not sure now. It's not that high. It could be somewhere between 1% and 2%, but I'm not really clear on that at the moment.
Thank you.
You're muted, Josie.
Hi, it's Stuart Waugh from the New York State Center for Clean Water Technology. Thank you very much for your talk. I'm wondering if you could give us a rough idea in the cities and the larger towns how wastewater is managed in Kenya. What percent, if you have any figures, a rough idea, what percent of those towns would be sewered as opposed to treating the wastewater on site to different degrees? Thank you very much.
Yes, thank you. Yes, wastewater treatment hasn't really gone, very far in our country, and in this sense, we don't really recycle, and the wastewater normally is just treated and then discharged into the environment once it has been properly treated. In terms of coverage of towns, in terms of networked sewerage infrastructure, other than the big cities like Nairobi, most of them are like at about between 10 and 30%. So it's quite low. So on-site sanitation is still key, using septic tanks and pit latrines in the poorer areas.
Thank you very much.
Okay. So I have one quick last question from David Black, and he wanted to know if more airborne geophysics, ground penetrating radar, gravity, etc., is being done to close the gap between satellite-based surveys and other direct ground truthing.
Yes, right now, so there's some airborne geophysics going on, and it's being done over the entire country.
Yeah.
Although the main objective is the mineral resource rather than water.
Right.
We are hoping that we'll be able to get into this data in the coming years, maybe not so soon, but maybe in another 3 or 4 years when they declassify some of it, because right now it is classified information.
Ah, okay, okay. Well, thank you very much. This was wonderful, and we really appreciate you taking up your evening to talk to us.
Thank you very much. It was my pleasure.